probing the epoch of reionization, and also how we are trying to determine if galaxies really reionize the universe, the exact contribution of galaxies to this process of cosmic reionization. And by doing so, we're also looking at how the first generation of galaxies started to form at this crucial epoch. And of course, we're going to see how the JWST is going to help answer some of these fundamental questions later on in the talk. So to give you a bit of context, we are interested really in this epoch of reionization here, where the universe transitioned from a completely neutral state to a completely ionized state here. So this is one of the major transitions in the history of the universe. There was a global change in the state of the baryons in the universe. And this reionization, it's a very important process, but we still don't know the very sources that reionize the universe. It's still an ongoing quest. And of course, the first major transition in the history of the universe was the recombination epoch. We start with the Big Bang, and just after the Big Bang, the universe was in a hot and ionized state, and then the universe expands and cools down, and it allows the hydrogen atoms to recombine, and this is where the cosmic microwave background was emitted around 400,000 years after the Big Bang. And after that, the universe was completely neutral and filled with neutral hydrogen, and then the universe expanded and cooled down farther, and you have the first sources that start to form the universe and to ionize these small bubbles, and then these bubbles grow until they reionize completely the universe. So we are really interested to know first, what are the sources that drive cosmic reionization? This is the main question here that we are still trying to answer. Regarding when the reionization occurred, we have pretty much a good idea when it happens by basically tracking this ionized fraction of hydrogen with time. And this is a competition between these two terms. One of these is the emission, the ionizing emissivity of the sources that ionize the intergalactic medium, the neutral gas. This is the density of the hydrogen in the universe, and this is their combination. So if the atoms cool down enough, you will have the atoms recombining. So it's a competition between these two terms. To maintain the universe ionized, you need this first term to be basically bigger than this. And we try to follow the evolution of this ionized fraction as a function of redshift, which is basically as a function of time. Looking at redshift is basically the light emitted by this the distant sources that shifts towards the red. So we are really looking more and more into the red wavelengths by looking at these galaxies that are very distant. So this is what it looks like when we track the ionized fraction of hydrogen in the universe. So you start with a completely neutral universe until you have a completely ionized universe here from redshift 12 to redshift 6. This is basically from a universe having a few hundreds of million years after the Big Bang to this, which had redshift 6, which corresponds to 1 billion years after the Big Bang. And you see that this gray area is a constraints we have from the Planck satellite by studying the CMB, the cosmic microwave background. What happens is that the CMB actually scatters on the free electrons in the universe if you have hydrogen, ionized hydrogen, and we can estimate the ionized fraction thanks to that. And you have an estimate from Planck, but you have also other probes of the ionization from, for instance, Lyman alpha forest, which is the absorption of Lyman alpha by the intervening neutral gas between the observer and the galaxies or the quasars, for instance. And you have also simulations that are more realistic where you have this smoother transition from the neutral to ionized gas. So now this gives you the answer to more or less when the reionization happened, but we still don't know what are the sources of reionization. And there have been a lot of potential candidates for this reionization, and two of them are very important. One of them was supermassive black holes. That could be a really good candidate because they emit what we call quasars in this instance, because they emit very energetic radiation able to ionize the universe. And because their spectrum is very hard at the short wavelength, so you have also an escape fraction. This radiation emitted by quasars escapes easily the quasars to reionize the gas in the universe. The only problem with quasars is that you don't have enough of them during the epoch of reionization. And you see the evolution here of the number density of quasars or AGNs you have from local universe to the high redshift. And we get to the interesting epoch of reionization. You see that you don't have any more quasars. So it means you're not going to have enough contribution from quasars at those epochs. So we turned our interest to the other interesting candidate, which is now the best candidate for reionization, which is galaxies. And to know if the ionizing emissivity of galaxies, to measure this ionizing emissivity, you need to measure many parameters. First of all, you have this, I'm just showing you here a spectrum, a typical spectrum of a galaxy. What we measure when you look at high redshift galaxies is the UV luminosity, this UV continuum, around 1500 angstrom in rest frame. But this UV radiation is not energetic enough to ionize the hydrogen. It's below 13.6 electron volts. So you need to transform this, to convert this UV radiation to the intrinsic ionizing flux in galaxies, which is below 912 angstrom in galaxies. This we cannot observe directly because it's absorbed by the hydrogen we are trying to reionize, of course. So we need to know this factor between the UV and the ionizing flux. Once we measure this, we need to measure the escape fraction of this ionizing flux within galaxy, because part of it is absorbed within the galaxies before going to the intergalactic medium and reionizing the universe. So basically, we need to measure these three parameters in galaxies and estimate the total emissivity of galaxies and see if they can do the job or not. So we do this in three ways. One of them is to measure the UV directly in the galaxies during the epoch of reionization, because we can detect them at redshift 6 to 10. So we detect those galaxies and we measure the UV luminosity. For the conversion factor from the UV to the ionizing flux, we need to know more in details what's happening, the properties of galaxies. So we try to study galaxies that have the same properties as those high redshift galaxies, but more in the local universe at redshift 2, where we can do spectroscopy and analyze in details those galaxies. And then for the escape fraction, we cannot detect the ionizing radiation, as I was saying, so we need to observe this in local galaxies that have also the same properties of high redshift galaxies and see what is really the escape fraction of these radiations. And these three parameters will give you the total ionizing emissivity of galaxies. So to measure the first of these, so I told you we need to detect directly the galaxies during the epoch of reionization, and this is what we've been doing for more or less the last 20 years. And we've assembled large samples of galaxies at high redshift. And you see this is more or less the total area on the sky that we have, where we have deep observations sensitive enough to detect those high redshift galaxies. And you see it's a tiny area compared to the size of the moon on the sky. But still, what we are interested in is to expose for a long time, weeks in some of these part of the fields. For weeks, we expose with the most powerful telescope we have, which is the Hubble Space Telescope, to detect those galaxies. And once we detect the galaxies, there is a very useful quantity we can measure, which is the UV luminosity function. The UV luminosity function is basically the number density of galaxies as a function of their luminosity. Well, this is the magnitude. So you have bright galaxies here, and you have faint galaxies here, and this is the number density of those galaxies. So you can see that we have more or less pretty much good constraints on the shape of this UV luminosity function, because we have nearly 2,000 galaxies detected at that epoch of reionization. And more importantly, you can see that this luminosity function evolves with time, with redshift. So this evolves from redshift 6, for instance, 1 billion years after the Big Bang to a few hundred million years after the Big Bang. So you see the evolution in the shape, in the number density of these galaxies. And you can notice that we have many more faint galaxies than massive galaxies. So this is important because if you want to measure the total emissivity of galaxies, you need to take into account the contribution from these faint galaxies because they are more numerous than the massive galaxies, the bright galaxies here. Once you have, and by the way, this luminosity function also holds a lot of information about galaxy formation processes, and we're going to come back to this later. But now, once we have the UV luminosity function, we need to measure the total emissivity in the UV of galaxy. So we just need to integrate this UV luminosity function as a function of the luminosity of the galaxies. And you see here the cumulative UV luminosity density of galaxies at redshift 6. And I'm putting here the limit. This is the limit, really, of our observations. This is the deepest observations obtained with the Hubble Space Telescope. So this is the best we can do. And you see we fall short of reaching this threshold where we know there is enough emission to reionize the universe. So we are lacking photons. We're lacking the contribution of those faint galaxies here. So we need to push farther to account for this contribution of faint galaxies. So to do so, we have also other cards up our sleeves. And one of those is gravitational lensing. So when we have massive structure in the universe, in this case, massive galaxy cluster, it's a cluster of massive galaxies here, so it bends the space-time, and it bends also the light coming from the distant sources behind this lens. So it acts really as a lens, and most importantly, it's going to amplify the flux of these distant sources. So it's going to boost the flux and the detection limit of our telescope, and we can detect fainter galaxies than just only with the telescope. So here's an example of a massive galaxy cluster that acts as a lens, and you can see, of course, all the effects of gravitational lensing. You see these big arcs of the distorted distant galaxies. This is a big one, a big spiral galaxy distorted by the lens. And we made also the community also tried to take advantage of this gravitational lensing by doing a large survey similar to what I was showing in blank field. This is empty sky, but here we are using the gravitational lensing in 6 galaxy clusters to use this amplification from lensing to detect fainter and fainter galaxies in the universe. And once you have that, you need also to calibrate your lens to know exactly what's the magnification in each point of your cluster and to calculate the intrinsic luminosity of galaxies once you correct for this amplification. And this is a lensing model we built. So you have here in color actually going from the blue to the red, the amplification factor. So in blue you have almost 0 amplification, but when you get close to the massive structure of the galaxy cluster, here in red, you have amplification factors that go up to 10 or 100. You can amplify your flux by 100 in these red areas. And you can also have, you can see the shape of these lines, which give you the direction of the distortion of your galaxies. You can know how much your galaxies are distorted, and you can reconstruct the actual shape and size of the galaxies. And of course, nothing comes for free in this universe, so you have an amplification factor by the gravitational lensing, but you have also a shrinking in the area, because if you look at the galaxy here, which we call the image plane, this is what you see in the sky, but the actual size of the area you're looking at is much smaller behind the cluster because of this lensing. So if you have this big area, you will have a smaller area you're looking at actually at higher redshift. So I give you an illustration here. One of the galaxy clusters, this is what you see on the sky. But at redshift 6, when you reconstruct the area you're looking behind with a lensing model, this is the area you are looking at. It's very tiny compared to what you are looking at in the image plane. So you also need to take into account this shrinking of the lensing into your galaxy counts and UV luminosity functions during the epoch of reionization. Another factor also we need to take into account is the differences, the systematics in modeling these lenses. So here's an example where we took different teams, produced different models. So we tried to compare what this model produce as an area in the source plane at redshift 6 behind the same cluster. And you see that the shape is more or less the same, but there are big differences in the magnification and also how these amplification are distributed in the source plane. And this gives you also systematics that you need to incorporate into your models and also in your determination of the luminosity function of galaxies. And finally, a small detail of lensing also is that for the same galaxy, you can have multiple images, so you have to be careful not to account multiple times for the same galaxy. So for instance, you have a spiral galaxy here that you are looking at, and you have another spiral galaxy here that you are looking at, which is the same galaxy. These two galaxies are the same, and you have even a third image here of the same galaxy. So 3 images of the same galaxy. So you have many of these phenomena in the cluster, so you have to take into account all these multiple images in your lensing. So once you have done that, this is what you get actually in terms of your UV luminosity function. You see this is the limit I was showing you in the deepest fields with the Hubble Space Telescope, and this is the improvement we get. So almost 2 magnitudes deeper than the blank fields thanks to the lensing, and you can see that this shape of the distribution is still very steep. So it means we are detecting more and more fainter galaxies at higher redshift. It means that you cannot ignore the contribution from fainter galaxies because they are more and more numerous in the universe. And once you have this, you can also do the same game as before, integrate the total luminosity of these galaxies to see now if it's enough or not to reionize the universe. And this is what you get now for this limit. So you see we are entering now the regime where galaxies could really potentially do the job of this reionization. Of course, we still have uncertainties here in the yellow area, but also when I say galaxies can reionize the universe, I put a little asterisk here. This means that we have also used canonical values, assumed values for, remember, the other 2 parameters I was telling you about. The conversion factor here and the escape fraction, we use just canonical values, so we need to estimate better these parameters to really tell what's happening here if galaxies produce enough energetic photons to reionize the universe. And we're going to see now how to measure, of course, these other parameters, like this, what we call here the ionizing efficiency of galaxies. Once you know the UV, how much ionizing UV you have in a galaxy. So trying to measure this parameter, it turns out it's very interesting also, because when you look at these faint galaxies I was showing you, which are much more numerous, they are actually more representative of galaxies at higher redshift than the massive galaxies. Well, it turns out the star formation proceeds in a different way, completely different way in small galaxies than in massive galaxies. For instance, when we look at small galaxies, star formation proceeds in bursts, short bursts of star formation, it shuts down, and another burst of star formation, and it shuts down, rather than a smooth star formation rate as a function of time in massive galaxies. And this has important implications on the measurement of these parameters. You can have a factor of 10 difference from here to here. So we really need to measure exactly how star formation proceeds in the small galaxies to be able to measure this. Here's, for instance, a numerical simulation of star formation in galaxies. This is a low mass galaxy, 10 to the 7 solar masses galaxy, and this is 10 to the 10 solar masses galaxy. And you see that star formation as a function of time evolves differently from here to here. You have very short successive bursts, and you have maybe one burst here, and it lasts longer in massive galaxies. So to do so, we also use the Hubble Space Telescope, but this time in spectroscopy. We combine many programs here doing imaging in the UV and spectroscopy. And one of the very interesting and powerful way to study galaxies with Hubble is what we call grism spectroscopy. So it's slitless spectroscopy. It means we don't put a slit to obtain a spectra in one galaxy, but we disperse the whole field that Hubble observes to obtain spectra. It means you get a spectrum for each object in this field. So this is how you can assemble thousands of spectra for galaxies and do a statistical study of these properties and measurement of the ionizing properties of galaxies. And to measure this stochastic star formation, or what we call burstiness in galaxies, this bursty nature of star formation, we measure the ratio between two star formation rate indicators, which is the H alpha, which is the combination line of hydrogen, H alpha, and the UV. So the ratio between the two, H alpha and the continuum, the UV. It turns out that when you have a burst of star formation, the H alpha emission is going to react immediately. So the H alpha is going to increase immediately after the burst, but the UV is going to lag behind because the time scales of the stellar population is different. So if you have a burst of star formation, you're going to have an increase in this ratio. But if you have an equilibrium of star formation, a smooth star formation without burst, you're going to have this ratio more or less equal to 1 in this gray region. So what we see is that the bursts of star formation appears to be preferentially observed in low-mass galaxies. As you can see, the ratio is much higher in low-mass galaxies here than in massive galaxies. So of course, this is what we suspected. But when you look at the models of star formation in these galaxies, it's completely different, because for lower mass galaxies, you see that this ratio is lower than the equilibrium. So this is most likely caused by the parameters used in the simulations, in the models of galaxy formation. It means that the duration of these bursts, or even the interval, the time between the successive bursts, is not the right one in the simulations. So based on this, we need to revise these parameters in the simulations to take into account what we are observing, this evolution of the burstiness as a function of stellar mass when we go from massive galaxies to low-mass galaxies. And this is basically also because for a long time, we were really studying only massive galaxies because they are easily detected because they are bright galaxies. So much of our understanding of galaxy evolution was based on massive galaxies. And now that we are able to detect these low-mass galaxies, so we see they are completely different in behavior, star formation behavior, than massive galaxies. And now it's interesting for what we're trying to measure, the ionizing efficiency, because it's directly related to this ratio of H alpha to the UV. So if you have a big variation in this one, so you're going to have also a large variation of the ionizing efficiency of galaxies. So this is what we measure now, the ionizing efficiency in galaxies as a function of mass. And you can see that increases also, of course, towards low masses. So when you go from massive galaxy to low mass galaxy, you have a factor of 10 difference. So instead of using the canonical value that I was showing before, which was based on massive galaxy, you need to take into account this evolution with mass to construct a more realistic scenario for reionization. And if you look also as a function of redshift, as a function of distance, so as a function of time, you go here from close by galaxies to the epoch of reionization, you see also that this ionizing efficiency increases towards the epoch of reionization. It means that galaxies at the epoch of reionization have a higher ionizing efficiency. So all of these combined tells you that low-mass galaxies, tiny galaxies, can have really a major role to play in the reionization of the universe. And so lastly, finally, the last parameter I wanted to show you, the measurements, is the escape fraction of this ionizing radiation that is able to escape the galaxies to reionize the universe. So here again, we're using the Hubble Space Telescope to look at the local galaxies, close by galaxies, because this is where we can detect this ionizing radiation, otherwise it's absorbed at higher redshift by the intergalactic medium. So this is an example of a galaxy. We are looking at redshift almost 0, close by galaxy. So this is the image of the galaxy. It's a very tiny galaxy, and this is the spectrum, and this is the interesting radiation we're looking at, the Lyman continuum below 912 angstrom in the rest frame. So this is the radiation that is able to ionize hydrogen atoms, so able to reionize the universe. And by modeling the intrinsic emission, we can actually estimate the escape fraction of this radiation in those galaxies. And we also try to look at the behavior of the escape fraction as a function of galaxy properties, because we cannot take one value of escape fraction for the whole spectrum of masses we have in galaxies. Massive galaxies, it turns out, have low escape fraction compared to low mass galaxies, as you can see here. So the high escape fraction are preferentially seen in low mass galaxies again. And here for massive galaxy, you see the escape fraction is low, it decreases to 0 here. Again, that tells you that the escape fraction is higher in low mass galaxy, tells you that low mass galaxies, again, are very important for reionization. And the same here, if you look at the escape fraction, this is as a function of compactness of the star formation. It means that the radiation, ionizing radiation, escapes better from these tiny galaxies if they have compact star formation regions instead of big, massive galaxies, star formation spread out all around the galaxy. So now, to summarize, we have these 3 parameters. We measured the UV directly in galaxies. We are reaching this limit, the threshold of galaxies where galaxies can reionize the universe. And now we need to push farther down to detect even fainter galaxies that we are able to detect even with gravitational lensing. But also we need to constrain more these parameters better to see where this threshold can change, actually, where galaxies can reionize the universe. If we have more realistic values for these parameters, then we can put a more firm threshold for this reionization limit. So how do we do this? Now we come also to the interesting part of JWST. JWST is going to probe exactly this region 2 magnitudes deeper, so we're going to be able to detect these missing galaxies, very faint galaxies. And with spectroscopy also on JWST, we'll be able also to measure this parameter, the ionizing efficiency, for instance, in these galaxies. So just a word now on the JWST. Now that it's really around the corner, now we're going to have the first observations of the JWST starting in June. So this is JWST in the lab. And rest assured, it's not the final shape of JWST. This doesn't look like a telescope because it's folded. So once it's unfolded, this is the JWST with the primary segmented mirror, the secondary mirror here. And this is the sun shield that protects the telescope from the radiation from the sun. And yeah, and this is the sun shield, so it's really a huge sun shield. It's the size of a tennis court, and you can see the size compared to these engineers here that we launched into space. Of course, it's folded in the Ariane rocket, and then it unfolds in space. And everything went to plan in space. Everything unfolded, the mirrors, the sun shield, and the secondary mirror as well. So now the JWST is at L2 point, which is 1.5 million kilometers from Earth, and it's not actually on a fixed point, it's orbiting the L2 point. And it needs some adjustments with the propulsion to maintain the JWST around this point. And of course, it also orbits the sun at the same time. Yeah, I think this is just a cool image where you see actually the JWST here taken from a telescope from Earth. When it was going towards the L2, you can see it traveling towards its final destination. And this is the live status of JWST. That it's a screenshot just took 1 hour ago. So you see the temperature of JWST. Right now it is cooling down because it needs to reach a very low temperature to operate, because it's operating in the near infrared and the infrared. So it's, you need to cool down the telescope to avoid thermal emission from the instruments and from the telescope and from everything, really. So this part of the telescope is very cold. Right now, it's minus 230 Celsius. And you have a hot part here, which is exposed to the sun, protecting the telescope, which is around the 40 degrees here. And this is what we call the first light of JWST. You see here a selfie of JWST taken by the secondary mirror in a very special setup to take the image of the primary mirror here. So this was the first light taken like a couple of weeks ago. And this is the image of one star we are using to align all the individual segments of JWST. And at the end, once all the segments are aligned, you should be able to see only one single point, which is the star, very sharp single point source of the star. So this is a process which is ongoing, the alignment and the phasing of all the mirrors of JWST. This is the focal plane of JWST. So all the instruments are lying actually in the same focal plane. So you have a NIRCam, which is mainly imaging, MURI, which has also imaging and spectroscopy. You have NIRISS, which is mainly slitless spectroscopy, as the one I was showing you with Hubble. And you have NIRSpec, which is a multi-object spectrograph to take spectra of multiple objects at the same time in the sky. I think one of the main advantages and the big step forward we made with JWST is summarized in this image, where you see the gathering area of JWST, which is related to the size of the mirror of JWST, and also the wavelength where the telescope operates. So we use most of the time to compare JWST to HST, saying that JWST is the successor of HST, but we really should compare JWST to Spitzer, which operates also in the infrared, and you see that Spitzer is really tiny mirror compared to the JWST. And that means it's going to give you a huge leap forward in sensitivity, but also in resolving power. You're going to have a high spatial resolution with JWST. So I give you the two important facts here. This is the sensitivity as a function of wavelength. So this is really the limit of the flux you can detect with JWST. So this is a low flux, this is a high flux. So you see JWST, you can detect much fainter object here than Spitzer, for instance, 1 or 2 orders of magnitude fainter than Spitzer. But it's not the only thing. So the big sized mirror also gives you better spatial resolution. This is an image of few galaxies with HST, with Hubble. This is the same image with Spitzer, and this is at the same wavelength with JWST. So you see the big difference between Spitzer and JWST. You have nearly the same resolution as Hubble, but at longer wavelength in the infrared. So it's going to be really a game changer in terms of studying high redshift distant galaxies. So I'm going to mention one of our accepted programs with JWST. It's going to start in this summer to try to detect these faint galaxies during the epoch of reionization, the first generation of galaxies, thanks also to gravitational lensing. So we combine JWST and, again, lensing cluster, which is here Able 2744. So we, in the first step, we do a very deep imaging, and then we come back 6 months later by selecting the interesting galaxies we detect in imaging. We do spectroscopy with NIRSpec to analyze all the physical properties of these galaxies. And this is to tell you the improvement compared to the other programs we've made with Hubble, for instance. This is the depth in magnitudes. It means this is bright, and this is faint galaxies. And this is the area on the sky we are probing. And this is our program here, and you can see it's in the ballpark of all the programs comparable to other programs in terms of sensitivity and area. But once you take into account the gravitational lensing I was talking about, the intrinsic limit that you're going to reach, of course, is going to be much lower. So this is an unprecedented limit, like 2 magnitudes deeper than we've ever seen, even with Hubble and lensing. So here we're going to be able really to detect extremely faint galaxies, but also very distant galaxies. So for instance, The limit now is really around redshift 8 or 9, which is 500 million years after the Big Bang. But with JWST and lensing, we're going to be able to go close to 100 million years after the Big Bang. So this is the area, the regime, where we really think that the first galaxies should be forming around those epochs. So here's an example of all the spectra. These are simulated spectra of what we can see at high redshift with JWST. So for instance, you can see all the other recombination line in the optical, not only in the UV, but also in the optical, like O2, H beta, at redshift almost close to 15. This is just 100 million years after the Big Bang, and you can do really physics and try to measure the physical properties like the star formation, the age, the mass, the dust content, the metallicity of all these galaxies for the first time. And one of the interesting science cases is to see the efficiency of star formation that evolves in these galaxies as a function of time from early on redshift 13. In these epochs, we don't have any constraints really, so we have many models that try to model the evolution of star formation efficiency in galaxies. So here you have pretty steady efficiency in galaxies, and then the models really diverge here, and we don't have any clue what happens. And here with JWST, we're going to be able to discriminate between all these star formation efficiency models thanks to these observations. And another, I was telling you about when I first started about the UV luminosity function, how it holds also important information about galaxy formation models. You see here historically in numerical simulations where when we tried to reproduce the formation of galaxies, we failed really to reproduce the UV luminosity function of galaxies. So you see here in red the numerical simulations of this UV luminosity function, and in blue what we observe actually. So you notice big differences here for massive galaxies, and you see big differences also for low mass galaxies. So for massive galaxies, we found out that you need to take into account the feedback from AGNs, from black hole that emits radiations and heats the gas and prevents further star formation. And here in low mass galaxies, it's more explosion of supernova that expels the neutral gas that try to form stars, so you have less star formation again here. So if we study really the exact shape, for instance, of this faint slope here of the UV luminosity function, it can tell you how star formation proceeds, and also how feedback from this supernova and stars proceeds into shutting down star formation in these early star-forming galaxies. So the question really for our measured luminosity function when we push farther is to know what happens then if the feedback is very efficient at shutting down star formation. So this luminosity function is going to go down because you don't have enough star formation in these smaller galaxies because supernova and stellar radiation stops star formation, so you don't have enough tiny faint galaxies here. Or it just flattens out a little bit, so you have intermediate feedback strength, or it keeps on going, it's very steep, and the feedback is not efficient enough to stop star formation. So you're going to have very strong constraints in the galaxy formation model just from the shape of this faint end of the UV luminosity function. And of course, this is where JWST is going to help us put these constraints. And another interesting approach to this problem is to use local galaxies as fossils for high redshift galaxies, for the distant galaxies. Because in the local universe, you can take really the low mass galaxies in the local universe, you study their star formation history, so you can track back their luminosity for their progenitors at high redshift. And then you can construct the UV luminosity function for these progenitors at high redshift. And when you do that, if you keep this steep UV luminosity function down to faint magnitudes, you're going to have this, of course, at those redshift. But from the constraints from the local galaxies, when we project that back to high redshift, this is what you get. So there is a big difference between these two disagreement. What it means is that if you have this steep faint end, you have a lot of galaxies at high redshift, you're going to overproduce local galaxies later on, 13 billion years later. So if you keep this faint slope very steep, you overproduce local galaxies, so there is a problem. So you need this slope at some point needs to flatten down to be able to match this. And if you do that, actually, if you flatten a little bit from here -2, flatten it out to -1.2, for instance, and then you have a match between local galaxies and high redshift galaxies. So for sure, you have to flatten out at some point this curve to match the local observations of tiny galaxies. But you have also to be careful, because if you flatten it out too much, you're not going to have enough radiation to reionize the universe for these galaxies. You're going to have this problem where you're not going to reach the threshold because you don't have enough faint galaxies to produce the lacking contribution to reionization. So this is a trade-off, actually, and it's going to be interesting to see the actual observation, what happens to this regime here. And the extreme part, if you flatten this, or if you have a turnover here, as some observation actually already suggests here, if you have the turnover here, it means you shut down star formation in galaxies within absolute UV magnitude of -13. That means that these galaxies lie in dark matter halos of 10 to the 9 solar masses, in the host, the dark matter halo host of these galaxies. 10 to the 9 solar masses, and the problem is that we don't know, no numerical simulation, no galaxy formation model can shut down star formation at those limits. So we don't know how to do that. So if you have a turnover here, you have a big problem for our models of galaxy formation. And for instance, I'm showing here the different cosmological simulations and the models of galaxy formation. And you see that they're pretty consistent in most of the regime here of UV luminosity function of the masses. But when you get to this low mass galaxy, so you start to see an order of magnitude disagreement between all those models. Because all those models use different recipes for the feedback. For instance, to shut down star formation, you have feedbacks, for instance, that is related only scale to star formation, for instance. You have feedback that includes the explosion of supernova that is related to the initial mass function of the stars, which means the distribution of your stars in the first galaxies. And you have also other that use ad hoc recipes for star formation, and you have others that add MHD, others that have cosmic rays. So you have many recipes to actually that actually enter in these feedback processes that regulate star formation. And no surprise, you have a lot of differences. And this is where really the observations are going to, again, put strong constraint on all these star formation, galaxy formation models. I still have time, right? 8 minutes, okay. And then I'm just going to mention maybe this, another interesting way also to look at the UV luminosity function is to probe through the luminosity function the nature of dark matter. When you look at the distribution in halo mass of the dark matter, the models of dark matter, you see that when you get to low masses, the distribution depends on your model of dark matter also. If you have a cold dark matter, you're going to produce a lot of low mass dark matter halos. And if you have a warm dark matter model, you're going to produce less and even a turnover. At some point, you're not going to be able to have enough low mass dark matter halos with this warm dark matter model. And you can, of course, translate this to the UV luminosity function by applying a star formation efficiency recipe. And this is what you get at redshift 7, for instance. And again, all the dark matter models are in agreement here. But when you get to low masses, they start to diverge again. So you have big differences here to -14, -13. So depending on the UV luminosity function you get, you can put a limit of your dark matter particle, for instance, model. Yeah, and this is where the regime that we'll be able to probe also with JWST. So you see that there's a lot that you can learn from just the shape of the UV luminosity function in these galaxies, and you can extrapolate that to dark matter, the nature of dark matter. You can extrapolate that to the formation model, the feedback models you put in galaxy formation, and also to the local galaxies as a probe for the distant universe. And of course, I was mentioning only JWST, but you have a lot of future facilities that are going to work in synergy with JWST. For instance, you're going to have Blue Muse, which is a new spectrograph is going to be installed on the VLT, Very Large Telescope at ESO, which operates in the blue, hence the name. So you're going to be able to put better constraint, for instance, on the parameter of escape fraction. You have Moons, also a near-infrared spectrograph on VLT. We're going to be able to assemble a larger sample of galaxies at high redshift in the infrared, so measure really the ionizing efficiency of these galaxies. And we're going to do better even with Mosaic. That's going to be on the extremely large telescope in few years. And you have also complementary probes of the epoch of reionization, like SKA, the Square Kilometer Array, which operates in the radio. So you're going to have, you can probe the state, the other part, the other side of reionization by mapping the neutral hydrogen this time through the 21 centimeter line. So you're going to map the distribution of hydrogen. You can cross-correlate with the distribution of galaxies that ionize the universe. So these two probes can tell you the complete picture of the process of cosmic reionization and how it evolves with time. And we'll have also the ESA mission, also Euclid, where we will be able, for instance, to detect a lot more galaxy clusters that we're going to be able to use as lensing clusters. And we're going to also be able to use Euclid to detect very bright galaxies at the epoch of reionization. And bright galaxies, we can detect them through the Lyman alpha emission. Lyman alpha emission is very sensitive to the neutral gas. If there is a neutral gas around these galaxies, it's going to absorb Lyman alpha. But if you have an ionized bubble around the galaxy, there's going to be a shift between the rest frame of Lyman alpha and the hydrogen atoms, and then the Lyman alpha emission can escape if there is an ionized bubble. So by detecting these bright galaxies during the epoch of reionization, it tells you the distribution of these ionized bubbles that you discovered during the reionization. So you have really three complementary ways to map cosmic reionization. And I can maybe now just summarize what I said for the whole talk, but these three plots really tells you how important it is to probe this regime of low-mass galaxies at high redshift during the epoch of reionization, thanks to gravitational lensing and also the future large facilities like JWST. We're going to be able to probe really the nature of the feedback that shuts down star formation or makes star formation inefficient in the first galaxies. You're going to be able also to estimate directly with precision the exact contribution of galaxies to cosmic reionization, and finally answer this question, the outstanding question: what are the sources that reionize the universe? And then, of course, you can discriminate between all the galaxy formation model, and most likely we're going to be able to revise all the recipes we put into these numerical and cosmological simulations and better understand how galaxies, early galaxies, form. And I think I'm going to stop here. Thank you.